So you've gone on Google Classroom, you downloaded the file. Now we're going to go over this. You may have done this a little bit in middle school. We're going to go back when we go in greater depth. Wednesday, Tom will go into more with West Point Bridge Designer in a deeper dive than we'll get to tonight. Tonight was about installing software and explaining the science principles behind it. Remember, we have a lab Thursday for Thursday nighters, and we have labs Saturday. All right. So you have bridge foundation. Bridges form with compression. They push in either end like this. Tension, they pull apart. Think of a rope. You can pull a rope. You really can't push a rope. And then you have shear. One going this way, the other one going through the top. And now we're going to go to this one. So something else I want you to try. It's a forces lab. I'm going to copy it so you can get to it. And I'm going to copy and share it for you right now. But I do want to get this to everybody's in here. Send to all. Yeah, I did say I have a question. I have a question. All right, write your question. I did this for high school. Cool. What's your question? Yeah, if you want to show them this. Now, it can't be an all the time thing, but one time you wanted to show them, we can make it work. I'm not sure I can provide materials. I got to make sure I have enough materials for everybody that's there. Okay, great. All right, now let's go through this forces real quick. So everybody try this. You may have to tell it that allowed to use Adobe Flash, but go ahead and play with these and read. They also see it in real time. Notice compression is red. Tension, on the other hand, is in blue. And you can see the blue arrows right here. So go through each one. So give you a few moments to do that. Like literally just a couple minutes or so we can keep going. Raise your hand once you've done it. Raise your hands once you played through it. See another questions here. Nope. All right. So everybody's done it. Great. So let's go through it here. So just real fast. If compression, more compression, you're more pushing them in together. When you're doing tension, you're pulling them out. You're stretching them. Bending is interesting because really it's a little bit of both. Tension on the top is it's being pulled, over the top. And on the bottom, it's being forced together. So that's compression and tension. Sliding is one force, compression going in two opposite directions. Earthquakes are perfect for sliding. And then twisting, well, that's its own little compression, twisting in the material. See that with the Tacoma Narrows, when the wind starts going, we'll go over the force and start twisting that bridge. But the fact later you'll see that twisting sometimes saves a bridge. All right? So guys, make sure you're trying these labs as we do them. We're doing them for a reason. Let me do this. Let me go back. I'm just pulling up my high school version because we get into some math later here I want to use. All right, so now, we got force compression chair. We did the forces lab. Now, weight of the bridge itself. The bridge itself, that's considered the dead load. Live load is the people inside the bridge. All right. I'll just pull it up that way. If the load is still, it's static. Park car on a bridge. Dynamic, the load is moving, cars are motoring across the bridge. Thermals by atmospheric warming and cooling. When you come to the lab Thursday, if it's not raining or something, I'll show you that in our sidewalks. Loads created by the shaking of earth causes earthquakes. The wind is a very significant force, especially in the tall skyscrapers like in downtown Charlotte. There's load on labs. Again, you'll just see the weight of the structure. Dead load, that's the weight of itself, not really. Weight of objects is our elephants here. We put them on there. That's your live load. Soft soil, that's just misspelled. You can see it's shaped. You can on there, and in fact, I'll tell you what, go ahead and do temperature, earthquake, wind, vibration like we did the others, and then we'll talk about them real quick. Just take a few moments here to do this, please. All right. So by now, I'm hoping everybody has this. So soft soil, and so not surprisingly, you can strengthen it by putting in footers. That's where we put concrete in there. Sometimes you hear someone building some footers because they got soft dirt, and there's a way to measure it, and you put it in there so it's better. Then you have temperature. Like I said before, that's as much as expansion and contraction. Concrete is pretty sensitive to that. You'll see it move, but we can take that in consideration when we build things. You'll see it. Earthquake, not surprisingly, shake it around. You know, you strengthen it. They'll do solid walls or shear walls in the horizontal direction, so that tends not to shake as much. Wind load. On some bridges, this is why suspension bridges have spaces in them. They're naked. You can see the skeleton of a suspension bridge. It's so the wind blows through it. It doesn't blow against it. You just let it flow through it. And, you know, they'll use diagonal braces on them. That's usually good for many things, by the way, because now you're made a triangle there, and that's strong for a lot of reasons. Next one's a little bit weird. It's the vibrations over time. See how that's bending? It's going to get worse and worse and then break. All right? The Tacoma Narrows had that problem with vibrations. All right? So we did that. In terms of what you make a bridge with, probably the very first bridge was a tree had fallen over a creek, and early humans walked across the bridge. Now, the great thing about it is generally cheap. For the most part, it all handles both tension and compression well. It's fragile. You can burn a bridge down. And it's got maintenance costs all the time. You got to pay and take care of it. Why there's not a lot of wooden bridges around. Concrete, on the other hand, is cheap. Handles compression really well, like stone. It's fireproof, for the most part, weatherproof. It does not handle tension well. Try to stretch a rock. It's impacted a lot more by thermal loads. Okay? So there's some, and then, you know, like I said, reinforced concrete as steel can handle compression and tension. So instead of making a whole bridge out of steel or a whole mountain out of concrete, we take steel, put it in there, we call it rebar. We put it in the concrete, and so that it now handles compression and tension well, low cost. That's why if you go on 45, you see all those reinforced concrete bridges. It's fireproof, it's weatherproof. Yes, I know you get a concrete hot enough, it'll melt. But for the most part, we don't have to worry about that. Though in Atlanta, they just had a bad fire down there and it did. It got hot enough to melt the concrete. Then you have thermal loads. We said that's sensitive to that. Cast iron, on the other hand, forms in any shape you want. Regular concrete kind of does too. Handles compressions well. It's fireproof. Looks beautiful. It's expensive. Doesn't handle tension well. And the worst thing is it breaks without warning. So, again, beautiful, but breaks without warning, makes you very nervous. Steel, on the other hand, forms in any shape. It's compression and tension, fireproof, weatherproof. Its big issue is its cost. You know, if you keep painting that bridge, you take care of that steel bridge, it should last for a very, very long time. But so expensive is a further four. All right. And let's look at materials here. If you go back to building big, you go to materials. Go ahead, take a minute. You can work through the lab for a few moments. Up here, my thing, it says 8:32. Let's go to 8:36. Give you 4 minutes to work through that. All right, you got just another minute or so. I'm just going to give you another minute. Let's get started here in a minute. All right. So here we go, folks. What, again, cost is down here. Weight's pretty light. Weight means money because you got to transport it. The only reason the Romans could build the beautiful bridges they built is they had slaves to do the work. You know, they kept conquering the world and taking it. So it handles compression pretty well, tension pretty well. It depends which way you pull on the grains in terms of that. We taught applications. Makes for great roller coasters, in my opinion. Plastic is particularly pretty strong. It doesn't hold, you know, you can squash it, but it doesn't rip very well. But to do those synthetic plastics is super expensive because it can handle both compression and tension so well. You see them on tents. All right. Now aluminum's pretty strong. If you add some magnesium copper, it's as strong as steel. That's why we see them in airplanes. Brick handles compression particularly well. So if you push down there, it's a while before it breaks. Here it just takes a little bit and it breaks under tension. If you're building stuff just out of brick, it's pretty cheap. Concrete, well, there you go with concrete. Pull out here, oh man, it breaks. Now it breaks really bad. Same thing, again, tension just a little bit right on that side of it, compression down there. Reinforced concrete, it's a little bit of both. A little more expensive, but it's cheaper than steel. There's cast iron, then you put steel. So it gets much more expensive on that. And then on shapes, I'll go and give the talk, but you can just, the lab on that's pretty simple. Let me just show it. We'll do it to 1. Look at that. So it's under compression. This is a rectangle. See, everything's under compression. This bottom really wants to kick out. Arching, there it is. You can see the compression, especially if you put it against the wall or the side of a mountain. This really holds well. Triangle, compression here, and then tension down there. Oh, come on. The weight caused by the top sides to bend too much and they'll fail. Arches like to be pushed and squeezed. That's why it's stable, because really right down here normally is a wall or something they're going against. Now you get to that one, they'll start to fail. It's still standing because of the pulling force at the bottom, which is balancing out the compression. So this is a pushing, here's a pulling from the tension. But even then you can break it. All right. So we just said rectangle is least stable. It's best for compression, straighten with a buttress. That's buttress is on this side. This would be, all right, show you my mouse over here. Here and here. The sides of a wall all act like a buttress. See any questions before I got? No, okay. Triangle, our arch, rectangle, arch, and triangle. Triangle is the strongest at the points. It's the best. It's probably for weight and everything else. It handles both compression and tension. Is one we use quite a bit. Hopefully I'll get my mouse. There we go. I already did that. Real quick history of all this. Rome was the great bridge building culture. They was first to connect to the mainland and maintain their empire. They used the arch bridge, which used rock, which is cheap in terms of, you can find it everywhere, but it's labor intensive, and that's why they had to have slaves. Why do you think if a post and beam bridge, just a simple, what's so great about an arch and river traffic? What's so great about an arch and river traffic? Why do we like arches or suspension bridges for river traffic? Mind you, this probably went in after the bridge was made. They weren't putting up that. Yep, boats go through it, water to flow through it, absolutely. I saw a bridge, now it's 9 years. I saw it when I was on my honeymoon with my wife. She brought me back home. She's from France originally. We saw aqueducts that were 9 years old. All right, development of iron, here we go. Beautiful, but this just doesn't handle attention very well. The new big bridges. And then iron gave way to suspension bridges, which is really started when you started adding a little bit of carbon to steel. Carbon to iron to make steel. And, Golden Gate, beautiful bridge. Ever get a chance to go, there go. There, it is stunning. Now, the flexibility, though, in the suspension bridge means that it can also get spun and ripped. And that's what happened in the Comaneros. This bridge only lasted a few months. Now, the upside is that same flexibility helps the bridge survive an earthquake. So engineering is often a series of trade-offs, what you're trying to do. All right, so let's go here. You open yours up. We're going to jump over this. Next year, I want to do another competition. So let's go ahead, start your program up. Let's look at an example of one. So let me go down here. We're going to use 216. I'm going to pretend that's not even exist anymore. All right, let me see if I can get it back up again. Oh, shoot. Close this. All right. Hide that down there. Close that. Let's go here. This is great for tips. I would use the tips. I use them all the time. So I'll tell you what, raise your hand once you've got the program open. We're going to start going through it for the next 10 minutes or so. All right. Let's see how many more people are there. Come on, folks. Raise that hand once you have it. Let's see if there's any questions there. Yep. You've seen that video. Yeah, I bet you have. Actually, I'm going to have that video for, I hope some other folks can see it. All right, now. You can select several members by hitting the control key. You member list by member number, by member properties, or by load results. We'll see that in a little bit. So, how many people have their hand up there? All right, let's just do load to sample bridge design. Say OK. And then select the Brett Deck Truss. It's a classic. That should come up. Raise your hand once you've got it. Once you've got this picture right here. I'm going to see if there's any questions. Is there a contest? Well, we're going to have one. I'm going to give an Amazon gift card, the winning bridge score. We'll give a week or so. We'll give some dates here down the road. The old one doesn't exist. They didn't get any funding anymore, so we just keep using this one. Folks, I only have about half of us. I can't even go forward until we get more people. Caleb, Corey, Harry, Laura, Levi, Philip, Samuel, Sam, guys, raise your hand once you have it up. It looks like this. All right. Now, Mr. Dutoy will go through this in a big way. But there's the joints. There's the member tools. That allows you to take a joint and run it there to there. Let's look at this pointer. All right. So what this has, so I click here, it shows you the same member there. There's 1, there's 12, there's 2. You can see. And what it does, it tells you what the material is. It's carbon steel. It's a solid bar. It's 200 millimeters by 200 millimeters, or 20 centimeters by 20 centimeters. See that metric? Pretty nice. It automatically, so everything's in tens of metric. All right, now, there's your number of your iterations. Up here, you know, save your file, print your file. There's run the train. So here it goes. And it'll come back around again. I'm coughed up something here. Okay, pardon me. All right, so now we're in design. I just want you to use members list. Now, this selects all of them. And see when you're selected, they're blue. And somehow I just got rid of all of it, which is not what I wanted to do. Good. That'd been bad. You can go over iterations. There's a price there. And you can get, actually gives you a breakout where all the prices are coming. Then there's a status. There's your load test results. You can go back through there. Now, over here, when I select 1 over here, or 12, I should say, it tells the slenderness, and we'll get into what that means, compression, and it was under tension. All right? Okay, but what you can do, and you'll see as you get into this, you can start so you can get your test results going on this, or you can do it this way. If you collect on this thing here, you can go member details. It'll tell you the member size, all of it about it, and then it'll show you, there it is under tension. It's blue, it's constant. Whereas compression, as it gets longer, it's less stronger. You know, you can change unit cost, size in millimeters. All right, and that's about right for mine where we are right now with this. So then I can go to here, go to the next one. Now, you'll get a chance to design your own. We don't just keep using an example. And then what you can do is, that's a solid bar. I can make it bigger. It's 220, and then I can run the same test. Let's see what my cost is. It's 512. If I make it a little bit smaller, it's 509. I'm making it a little bit smaller, but let's see if it'll pass the test now. There it is. Now it's getting real red, but it passed the test. So in some ways, a real blue, you can see that you're stressing it out. But if I go back, I select that one again and I make it smaller. Price is going down. Well, let's see if it survives the test. Now see how bright red it is? Just the weight of the dead load on the bridge. Ooh, end of the truck. So everybody, go ahead and play with that a little bit. Don't save this bridge. You want to keep this original. When we do the animation, you could just see the dead load on the bridge. That thing was going to break already. So you want to keep playing with this. All right, so that's too small. And you can even say, see how it failed? It shows you that. Right? It's right there. So let's make it a little bit bigger. Let's see if it'll run now. It's red, but let's see. So we dropped the price for bridge to 505. And that's the kind of thing you start iterating your bridge. We'll go through the process and things, but that's what you start thinking about as you're doing your bridge. Any questions? I'm going to go down there. Oh, which bridge is this? This is a Pratt. I go, thanks. Oh, no. Good luck with your dance convention, Laura. Good luck. So, folks, a few minutes we have here. Let's go ahead and let you play with that, or go around and change them. Notice these are in red up here. These are compression. Notice the blue. They're in tension. They're being stretched. The red ones are being pushed down. For the sake of this, we argue either they're in tension or they're in compression. That is a simplification. All right. Now, last couple things to take a look at here. I mean, we're going to go into this much more detail on it. I just wanted you to see how you can change. It's got the material. You can play with that. Solid, hollow. We'll talk about the pros and cons of each of those down the road. You could do this with this. That's two that we made it. You can make it a hollow tube. Let's try that out. Well, that didn't work so well. Oh no. So that didn't work. But there's times the hollow tube makes a lot of sense, folks. That, fortunately, is not one of them. Let's go back to this. Go back to solid. All right, watch this. You could do. Now watch this one run. No problem. Took it like a champ. But you're going to see this even gets into, if you only make one piece of a bridge, that's expensive as well. All right, because I'm going out to a job site. I want all the same size pieces. I start making other ones. Look at the footer here that helps support this concrete. What's kind of cool about these things is this guy who designed that one, or when you design a real bridge, your name's associated with it for years and years and years later. You can actually go back to the Roman bridges and see they have the architect's names put in there. I'd just like to find that family tree. All right, are there any questions tonight? If there's not, I'm going to go ahead and stop. Wish you all a good evening. Remember, we have lab Thursday or Saturday this week. Lab Thursday or Saturday this week. All right? Take care, y'all. Bye-bye.